From antiquity, it was believed that the idea of empty space is a conceptual impossibility. Space is nothing but an abstraction we use to compare different arrangements of the objects. Concerning time, it was believed that there can be no lapse of time without change occurring somewhere. Time is merely a measure of cycles of change within the world. Then, in 1686, Isaac Newton founded classical mechanics on the view that space is real and distinct from objects, and that time is real and passes uniformly without regard to whether anything moves in the world. He spoke of absolute space and absolute time as a stage within which matter existed and moved as time flowed at a constant rate. It was understood that space and time tell matter how to move, but matter has no effect on space and time. The idea that space and time act on matter, but that matter does not act on space and time, troubled Einstein. Noting that light curved in a gravitational field, Einstein proposed that the mass of an object does indeed act on the space and time it exists in. Specifically, he proposed that the presence of matter curves space-time. This led Einstein to his theory of general relativity, which predicts the existence of black holes as objects so massive that light itself cannot escape their gravity. You'll recall explosions at the end of life for stars less than 5 times the mass of the Sun leave behind a white dwarf. In these stars, electron exclusion pressure is enough to counteract the inward force of gravity. Supernova explosions at the end of life of stars more than 5 times the mass of the Sun leave behind a neutron star. In these stars, electron exclusion pressure is insufficient to overcome the force of gravity, but neutron exclusion pressure is. But if a star is greater than 30 times the mass of the Sun, even neutron exclusion pressure won't do the trick. In fact, there is no known force that will counteract the inward force of gravity for such a supernova or hypernova exploding star. According to Albert Einstein's general theory of relativity, the star will collapse into zero volume and infinite density. This is called a singularity. This defines a black hole. It gets its name from the fact that such a singularity would create a gravitational pull that not even light could escape. The object literally becomes invisible. In 1916, Karl Schwarzschild, contemporary of Einstein, solved his equation for the special case of a non-rotating sphere. He found that although the diameter of the singularity is 0, the radius at which light would be captured depends entirely on the mass of the black hole. This is called the Schwarzschild radius, and it defines the event horizon. But it would be the rare black hole that doesn't spin. In 1963, Roy Kerr developed a general solution for spinning black holes. It showed that there is a second region beyond the event horizon that defines a volume around the black hole called the ergosphere. In this region, space itself is dragged around by the black hole's spin. It's called frame dragging. Also in this region, light can enter stable orbits around the black hole. This would produce a photon spherical shell encasing the black hole with the light from all the stars in the universe accumulated over the entire age of the black hole. It would be a sight to see. One of the things all rotating black holes have in common, besides the fact that we can't see them, is that matter flows in via an accretion disk. The exact mechanism is not yet fully understood, but we know that gamma-ray jets shoot out at the poles, carrying a percentage of the falling matter with it, at speeds approaching the speed of light.